We'll come back to the question, what if y is greater than L, in a minute. Not a difficult thing to adapt. But first, we want to add a little bit of labeling to this graph. The function is close to an exponential function with growth rate KL, provided that t is small. And that makes y significantly less than L. So that if y naught is a lot less than L, y remains a lot less than L for a ways. And that gives us something very close to an exponential solution. Then we get into a transition function. As y takes values that start to become close to L, well, the growth of this function decreases, and we begin to have a decrease in the slope, a decrease in the rate at which our population increases, and then we enter a region as we get very close to L where the value of y approaches L exponentially, so that we call that the region of exponential approach to the limit. So we begin to exponentially approach this limiting value. We want to relate this behavior, especially the small y behavior, to the behavior of a function with constant growth rate y prime equals ky. Now, when I wrote the logistic equation after having shown the equation for the constant growth rate, I used the same constant here. There are many reasons why one might do that. One is to keep things consistent in the notation, or at least maintain some consistency in the notation. Another strategy is simply that we're not aiming these clips at a specific textbook, and different textbooks will set up the logistic equation in different ways. And this way is sufficiently different from any other way that no one textbook has any great advantage over another. The process we use in solving the exponential equation, except for a few algebraic details, is very similar, and I want to come back to an interpretation that should be consistent with just about any approach that you encounter. So, let's recall that when we had a constant growth rate, y prime equals ky, that gives us exponential growth. That's something that's learned traditionally in first semester calculus course around the middle of the year, if not before. The logistic equation holds over a range of regions where we have the exponential growth, the transition, the exponential approach. Close to the, if y naught is less than L, then in this region we're close to an exponential function, so we want to see how this function is close to this function, how this function becomes close to a function of this general form as long as y remains significantly less than L.